Hello, in this video I'm going to take a closer look at fission reactors. So these are the nuclear power stations that are dotted around the world where we're splitting atoms in order to get an energy release from the higher binding energy of the products. So yeah, we're splitting atoms, not like the fusion reactors that we're still figuring out at the moment, where we're actually combining nuclei together to turn lighter elements into heavier ones. These are turning heavier ones into lighter ones. So the standard fuel for a fission reactor is uranium. As I mentioned in the previous videos, the most naturally occurring uranium is uranium-238. So of course 238 is the number of nucleons, and that's maybe, well, that's probably over 99% of naturally occurring uranium, but there is a small percentage, less than 1%, of uranium-235, which is a radioactive isotope. So if we can get enriched uranium, as in we can use a centrifuge or some other enrichment process in order to get the percentage of uranium-235 up to sort of 2 to 3%, then we're going to have a fuel source that we can use in a fission reactor. And pound for pound, you're looking at uranium being about 1,000,000 times more energetic than coal in terms of what we can release from it. So this is a great energy source that we've been able to use. But as we know, it comes with some drawbacks, but we'll get onto those drawbacks later on. So what are we trying to do with this uranium then? If we've got some uranium-235, we can initiate induced nuclear fission. This is the process that Meitner and Frisch came up with in the 1930s, where you fire a slow moving neutron into a uranium-235 nucleus, and that then creates uranium-236, which is then going to split. And it can split in a number of different ways. There's not just one outcome of this decay of the uranium-236. So one example is you can go to barium plus krypton. What would that be? 36. And then you get more neutrons coming out. So, and you can see all these numbers have got to add up along the top here. We've now got 3 neutrons have appeared. The energy that's getting released, because these nuclei here for the barium and the krypton, they're going to have higher binding energies. And it's that difference in the binding energies between what we started with and what we've ended up with that's the energy released. And that's released in the form of kinetic energy of these products. So all of these things are going to be moving around. So they're going to have a lot of kinetic energy. I mean, you are going to get some photons and things like that come out as well, maybe some neutrinos. So you've got various other things that are coming out. But most of it is in, 90% of it, thereabouts, is going to be in kinetic energy. We want to then use these neutrons here to continue the process. So this is where you get a chain reaction that, if one of those neutrons then goes and reacts with another uranium-235, then we're going to get another fission event. So that's what we want to be going on. How do we see this happening in the design of a reactor then? Because there's a couple of things that we need in this. I mean, you'll see with this equation, first of all, this is a slow neutron going in. These are fast neutrons coming out. So we need to do something about this. If these neutrons are going to perpetuate this chain reaction, we need to get the fast neutrons to become slow neutrons. Plus, we've got 1 going in and we've got 3 coming out. So we need to do something with managing those. So these are 2 key features of our fission reactor. Plus, of course, we need somewhere to hold all the fuel. And we need something in order to take the energy away. Right, so there's a lot of stuff going on here. So a basic design of one of the, what's known as a pressurized water reactor. These are the ones, they're used around most of the world as commercial nuclear power stations. They don't get used in the UK as far as I'm aware, but I think they're quite popular in the US, India, China, such like. So I think these are quite common reactors, these pressurized water ones, and they were originally the ones that were designed for use on nuclear submarines. And by nuclear submarines, we mean submarines that are powered by nuclear reactors, not necessarily that they've got nuclear weapons on them. So that's what's meant by a nuclear submarine. So you need some kind of container for the reaction to take place. It means you need the fuel in there, which comes in the form of rods. So you have these fuel rods. This is what's containing the uranium. So we've got fuel rods there. We're also going to have another set of rods. I'll put these in a different color. And these rods can go in and out of the actual reactor vessel, or whatever you want to call it. So these are the control rods. If I can write the word control rods. These control rods, as I say, they can move in and out, and they are there to absorb neutrons. So if you push them in, all the way in, they're going to absorb all the neutrons, or more than are required to keep the reaction, the chain reaction, continuing. So you push them all the way in, and it slows everything down to a stop, and the reaction stops. So that's how you can shut things down. If you pull them out, then it's going to accelerate the reactor, and you're going to have more and more, because all three of these neutrons that have come out can then go back and react with the uranium-235. So when when you flick the on switch of a nuclear reactor, a fission reactor, you want the control rods out, get everything going up to speed, and then move them in so that it's sort of one for one. So out of the 3 neutrons that get produced in this reaction, 2 of them get absorbed by the control rods, and 1 of them will interact with uranium-235 to get the next reaction, in which case we've just got a 1 to 1 to 1 to 1 chain, and all these extra ones are just getting blocked off by the control rods. So these control rods are made of things like boron and cadmium and things which have been shown to just be very good at collecting up, really snaffling up these neutrons. So that's what we've got going on there. But then we need to connect this up to some way of powering some kind of turbine, because we want to create electricity. So we have some pipes kicking around. So you have these pipes going off, which I've already drawn all over. So yeah, these pipes can connect up to some kind of big tank. And this big tank will also have pipes coming in and out as well. This is just, so in the case of the pressurized water reactors, this is all going to be water. So we're going to have water in here, which is going to act both as what's known as a moderator. So the moderator will slow down the neutrons. So these fast neutrons, when they start going through the water, so in this case this is water. It might be heavy water, so as in water made with deuterium for the hydrogen. But you've got this moderator. The moderator slows down the neutrons, so they're now these slow neutrons, what's called thermal neutrons, as in they're moving at, they've got less energy. They've got this sort of lower amount of energy associated with them. So that's what the moderator's doing there. But it's also, the water is then, it's got another role in taking the energy away. So you pump the water in, so water in here, and that gets pumped in. You've got a lot of energy here. That's going to heat up the water. So the steam is going to come out the top. So we've got steam coming out here. That steam then goes through the out pipe, and that goes steam to a turbine. We drive the turbine, creates electricity, and then the electricity shoots off. So we're using the water in 2 ways, one to slow the neutrons and then one to take away the energy. So that's the general idea. So quite often they ask you in exams to draw these sort of things. So you need to make sure you mention the fuel rods, the control rods, the moderator, and then how we're connecting up to the turbine. That's all the main stuff. So providing you can say what they are, the fuel rods are the uranium, the control rods are the boron, the moderators the water, and then we've got water in, heat it up, takes the energy away as steam, powers the turbine. There's your electricity. Wonderful. So it's a much simpler process, as you'll see if you look at my fusion reactor video, than what's going on with the fusion reactors. Obviously it gets hot because we're releasing a lot of energy and that's going into the steam. So it's hot from that point of view, but the actual reaction bit, we don't want to be hot. We want that to be quite, cool comparatively, the neutron. So it's a cool fission reaction. It doesn't require the high temperatures, the 100 million degrees that we need for a fusion reaction. We're not pumping things up to the temperature of the sun here. We're keeping things relatively cool and taking the energy away. Now, the problems that we've got with these fission reactors is not just these uranium-235 reactions that are going on. You've got other things that are happening. And this is where we start getting the environmental problems. So the uranium-238, that can start reacting with the neutrons. That captures a neutron. Now we've got uranium-239, which will beta minus decay in about 24 minutes. And that will produce some Neptunium-93. So, we've gone up an element. That will go up another element to Plutonium-293. So, and that beta minus decay again is about 2.5 days. So we're quickly producing plutonium while we're doing all of this. This plutonium has got a half-life of about 24,000 years, which of course is a long time, and it's toxic and it's radioactive. So we've got a problem here with this plutonium that's being produced. The plutonium itself can split in a fission reaction, and that will produce daughter nuclei, which are also hazardous. So we just get this glut of radioactive waste, this stuff that is going to be toxic for centuries or even millennia. And then what do you do with it all? So, you can store it underground. You can, stick it in big underground caves or something like that. But really, there's not a lot we're doing with this. We've either got to find ways of processing it better, ways we can use it for something, or we're just stuck with storing it and just, let's just stick it there and try and hope that it doesn't cause any problems. So there are definite issues with these fission reactors, and that's why they've been, or one of the reasons why they haven't been that popular with environmentalists over the years. Although in some ways they might have wished that we had more of these fusion reactors, because it might be better than the impact of burning all the fossil fuels that's been going on instead, because there has been a reluctance to build these nuclear power stations because of the waste that's produced. And then, well, what one's going to be worse? I mean, of course, you've got events like the Chernobyl disaster from the 80s as well, when you get a meltdown and, reactor goes boom and loads of people are killed and environmental catastrophe and all the rest of it. Not a good look either. We had something less catastrophic but still pretty bad going on in Japan at the Fukushima reactor as well. I mean, that was relatively recently, wasn't it? The last, 10 years ago or whatever it was. I can't remember what year that was now. So yeah, there's definitely issues from that side, but these power stations are now a lot more efficient, so they produce a lot less waste and they're a lot safer than they used to be. So particularly if you're building them in the right place. I mean, I know Chernobyl didn't have that excuse, but things like earthquakes and such like, which are quite common in Japan, do put an extra layer of risk over nuclear power stations. So I suppose on that note, I'll squeeze it in. I know I've already been talking quite a while, but a little bit of the history of what's going on with nuclear power from a UK perspective, and not just because I'm from the UK, but the first ever full-scale commercial nuclear power station was built in the UK in 1956. I mean, it was Calder Hall power station at what was called Windscale, what's now Sellafield. So Sellafield was a sort of the byword for dirty nuclear power back in the 70s and 80s. there were lots of protests there now. There's not a nuclear power station operating there anymore. They're trying to clean up the site after it being used for decades. But yeah, that was the first site. It was what was known as a Magnox reactor. So Magnox, which stands for magnesium non-oxidizing. It was the alloy that was used to clad the fuel rods. So you still got the uranium there, and it was clad in this magnesium alloy around those. Uranium, as I say, was the fuel. The moderator wasn't water in the moderator and the coolant in this case in these these designs, these pressurized water reactors. That isn't what was used in this. It was graphite was the moderator, and carbon dioxide was the heat exchange coolant. So yeah, a bit different there, and the UK kind of stuck with this graphite approach and not using the water in the reactors. So that was sort of the historical approach. The first design as well was a little bit different. Back in the 50s, there wasn't just an emphasis on producing electricity. The electricity was very useful, but the plutonium-239 that was being produced was then used in nuclear weapons. So this byproduct here was something that was being used. This was getting into Cold War times, and the UK wanted to have fuel for its nuclear arsenal that it was building up. So when the generation 2 Magnox reactors started being produced, they were more efficient versions of the original Magnox reactors, partly because there was no emphasis anymore on the plutonium production. So there are a lot of these power stations around. They've diminished somewhat in recent times. In 1997, which was the peak of nuclear electricity generation in the UK, 26% of electricity in the UK was from nuclear power stations. Now we're down to about 16%. And as you may have noticed in the news, there's continual wranglings about when and where future nuclear power stations are going to be built. And we've got, I think it's 5 or 6 operational power stations, something like that. There's one in Hartlepool. What we got? There's one near Edinburgh. There's of course Sizewell B in Suffolk, which is one that I've visited. One in Lancashire, I can't remember the name of it as well. The one in Edinburgh, I think it's Torness or something like that. So there's 5 or 6 of these around. I mean, you hear more about things like the big decommissioning processes that are going on at Sellafield. I mean, Sellafield has got this sort of hundreds of years plan of how to pull everything apart, because these early reactors were producing an enormous amount of waste compared to nowadays, where everything's much more efficient. They didn't really know how to handle the waste, how to store the waste. A lot of it was put in these big storage ponds, which were just big pools of water, and they'd put loads of stuff in there, highly toxic waste. I mean, there's estimations of over 1,000, maybe 1,500 kilograms or something of plutonium dumped in these pools. Some of it's in containers, some of it's now in just interacting with all the muddy sludge and sediment that you get at the bottom of these pools. Not entirely obvious what to do with a lot of them. I mean, you get some of them that are so toxic they don't want people spending more than 2 minutes near one of these big storage ponds because of the levels of radiation. And then, of course, that leads to more concern when you start getting photos coming out of, birds floating around on these pools and things, probably getting fried to pieces, the poor things. And, tales of cracks in the pools. Is this nuclear waste seeping out or not? So there's a lot of these news stories that get out, and, you never know how much of it is true, how much is overstated, understated, or whatever. But there are certainly serious issues with the amount of waste and at Sellafield, and then at these other legacy nuclear sites, Dounreay and places like this. I mean, they're all going to have waste that they would have produced, and there's always the issue of how do you handle it? How do you decommission these reactors after they've been working for 20 or 30 years? what do you do with all the stuff? So that's quite well, turned out to be quite a lengthy overview of fission reactors by the time I put all of the background in. So make sure you got a handle on the design of these things. I mean, they're always in the textbooks, and usually people have a pretty good understanding. It's fairly logical and easy to understand the process behind these fission reactors. So certainly have that. But all the ethical side behind this, and if you're thinking about the sort of things you can do as a career as a physicist, then there is a load of work in this sort of stuff. How actually building these things as an engineer, making them more efficient, cleaning up after stuff. Yeah, there's loads there. Physicists, chemists, and all the rest of it. It's a real area for the future and the present.